Okay, ladies and gentlemen, welcome to the lecture series on EC 393 Digital Signal Processing. In today's lecture, we shall be learning about the discrete Fourier transform. Now, before diving into the lecture, I would like to say that I haven't solved the mathematical problems on the discrete time Fourier transform, and I will try to do that at a later date. So let us start with the discrete Fourier transform. So I hope that you have studied the previous lectures, and if you haven't, I would earnestly request that you go back and study the previous lecture videos and come to this one. It will make life much easier. Now then, by now it is quite clear that in the analysis of a system, the characterization becomes much more clearer once we operate in the frequency domain. So in order to operate in the frequency domain, in order to operate in the frequency domain, we use various Fourier transform techniques. In the previous lectures, amongst the Fourier techniques, we have learned the continuous time Fourier series, discrete time Fourier series, continuous time Fourier transform, discrete time Fourier transform. And consequently, in today's lecture, we shall be learning about the discrete Fourier transform. Now, let us recapitulate the previous lecture where we derived the direct transform equation and the inverse transform equation for discrete time Fourier transform. So, for the discrete time Fourier transform, which obviously should work for any aperiodic discrete signal, will give us the direct transform equation as x of e to the power j capital omega, which equals to a running sum where n goes from negative infinity to infinity, x of n e to the power minus jn omega. And the inverse transform will be x of n, where we divide the period 1 over twice pi an integration which goes from negative pi to pi, x of e to the power j capital omega e to the power jn omega, d omega being our integral operator. Now, from these two equations, a very important bit of thought reveals to us ourselves. And I have clarified some of it in the previous lectures. I would repeat it now. One of them is that in the frequency domain, that is the omega domain, capital omega domain, the signal is continuous. And the argument behind that is, if you look close in the inverse transform equation, if omega was to be discrete, we need not take, or rather I should say, we cannot take the integral operator. In that case, we needed to use the summation operator, because in discrete domain, the area under the curve cannot be found using the integration. Now then, since we have taken integration as our summing operator in case of the inverse Fourier transform, it only dictates that the signal x of e to the power j omega in the frequency domain must be continuous. Otherwise, this integral operator becomes null and void. So, the first realization is that in frequency domain, the signal is continuous in nature. And the second concept is that in the frequency domain, the signal is periodic over a period of twice pi. Now, this statement is justified mathematically in the previous lecture. So, if you have any confusions, I suppose you should look back and consult the previous lecture video. Now, coming to the discrete Fourier transform, the only difference it has with the discrete time Fourier transform, so the only difference being, in the discrete time Fourier transform, in direct transform, we are giving x of n, which is a discrete signal, and consequently getting the output to be a continuous frequency domain, amplitude and magnitude. And in case of the inverse transform, we provide the signal with an continuous frequency domain signal. We provide the system with a continuous frequency domain signal, and in turn we are returned with a discrete time domain signal. So what I mean to say is that in discrete time Fourier transform, the time domain signal is discrete in nature, but consequently in the frequency domain, the signal is of course continuous. Now here lies the difference with DFT. What we need to do is make the frequency domain signal discrete, similar to that of the time domain signal. This is our primary task. So the only difference being DFT is to, or should I say, must have a discrete frequency domain signal. Now, why is that? Because all these operations that we have learned, we have computed it manually using mathematics, algebra, and various forms of calculus, which needless to say is quite tedious and rigorous in this respect. But in the practical scenario, what we do is we compute this form of transforms using a memory device such as computer or any form of calculator, that is the high-end calculator, what I mean to say. So in order to what should I say to make the signal acquainted with the computing devices, we must transform both the signals in the time domain and the frequency domain into discrete form. And this is because computer inherently can never store any form of continuous data. So one might ask that, sir, we have seen in MATLAB that we are able to generate a very smooth continuous sinusoidal curve using the computer. So the logic behind that is this curve is not continuous. There are very minuscule discrete samples which are so close together that it seems continuous. I hope you understand. So, in order to make the computer more familiar with the Fourier techniques, what we need to do is transform the signal into the discrete form, which, needless to say, will be very much beneficial in our processing of the signals for further reasonings. So before I go forward, I would like to point you out one more disadvantage of computer rather, is that if you look upon this integration sign, the computer memory or the computer processor does not have the capability to integrate a function in continuous domain. So what it does is essentially it does the summation but takes the limit to be infinitesimally small. So that is the algorithm that is used to operate integration. So I hope I am able to make you clear about the necessity of the discrete Fourier transform. So what we must do now is, our task will be to transform this continuous frequency domain signal to a discrete frequency domain signal. And in doing so, we must follow through another realization, which is that if a signal, it is somewhat a property of Fourier techniques, and you should remember it, that if a signal is discrete in the time domain, it will be periodic in the frequency domain, as we have seen in the case of the DTFT transformation. The signal x of n is discrete, but in the frequency domain the signal becomes periodic. And surprisingly, the converse is also true. That is, if the signal is discrete in the frequency domain, it must be continuous in the time domain. I mean, it must be periodic in the time domain. So the converse is also true. This will become much clearer as we proceed deep into the lecture. Up until now, but before going so, you must take my word that this statement is true. Now, moving on, how do we derive the equations, or rather I shall not say derive, how do we realize the equation for the discrete Fourier transform, that is the direct transform or the inverse transform? It is very much similar to that of the discrete time Fourier transform, and will be much easier if you have the clear grasp of discrete time Fourier transform. Now let us suppose we consider a discrete time signal that is x of n, and its DTFT pair is x of e to the power j capital omega. And let us suppose, say, x of e to the power j omega looks something like this curve, where this is our frequency omega domain, so this is 0, this is twice pi, and this is x of e to the power j omega. Let us mark it as figure 1. Now, in order to make this signal discrete, what we need to do, we must ask ourselves that question. And before doing so, I must emphasize that this signal 0 to 2 pi within this limit will again repeat after 2 pi. That is, the point 0 and 2 pi are essentially the same points. Now, going back to our question, how do we make this continuous signal discrete? In order to do so, we must rely on the concept of sampling a signal. What does sampling a signal do essentially? So the sampling of a signal is simply taking various samples, that is, not all the points in the signal, but taking certain points at a definite time interval and plotting the signal. So what we are doing is essentially sacrificing some of the data or information of the signal in order to understand the signal much better. This process is called sampling. So if we sample this signal, what we will get is something like this. Say, this is our signal, this is the 0 point, and this is the twice pi point. So this one is our first sample, this one being the second sample, the third sample, and so on, so this being the last but one sample. So let us divide this signal, say, into how many samples? N number of samples. So there will be n minus 1 number of slices over here. So if we divide the signal in n samples, so it is quite clear that the width of each of this, that is the width between two samples, will be nothing but twice pi over n. Because as you see, the whole width is twice pi and it is divided by n such that we get the width of the difference between two samples. I hope this is clear. Now then, if this is our first sample, so this point, let me mark it with a different pen. This point, I'll write it over here. Let it be twice pi over n. So what will be the value of the next point? So this point will be 2 times twice pi over n. This will be 3 times twice pi over n. And this one will be n minus 1 times twice pi over n, and this sample will be twice pi over n times n. So n cancels out, this becomes twice pi. I hope that is clear up to now. Now then, in our case, if the value of the first sample which is this one is 1 into twice pi over n, the second will be 2 times twice pi over n, and consequently the n minus 1th sample will be n minus 1 times twice pi over n. Now these samples can be written as a running sum of k times twice pi over n, where k is nothing but the integer value of each of the sample numbers. So obviously k will go from 0 to n minus 1, or it may go from k equal to 1 to n, because the total number of samples is n. So if we take the 0th sample to be the first sample, it will terminate at n minus 1. And otherwise, if we take the first sample to be the initial sample, it will terminate at n. The remainder will remain same. So for our ease of calculation, we shall be using this formula or this summation over here. Now let us move on. So referring to the direct transform equation, we get x of e to the power j omega to be equal to a summation where n goes from negative infinity to infinity x of n e to the power minus jn omega. Now if you look close in the previous figure, if this is our omega domain, in our case the value of omega is changed to k times 2 pi over n. So this being our new frequency operator, we can easily replace capital omega with the value twice pi by n times k, and consequently the direct transform equation becomes something like this: x of e to the power j twice pi over n k, which is essentially a function of k, because n in our case is a constant, because the number of samples we take must be a constant values. Pi is also a constant, 2 needless to say is a constant, and j of course is another constant. So what we can do is simply attenuate this haphazard term and simply replace it with k. So this is our new frequency domain operator. I mean frequency domain variable. And this will be equal to summation x of n e to the power minus j, omega is replaced by twice pi k, this n comes over here, divided by n. Now another important concept. What is that? The summation limit earlier was from negative infinity to infinity. But will it be the same in this case? Of course it will be not, because as I have said earlier, that any signal which is discrete in one domain must generate a signal in the which is periodic in nature in the counterpart domain. So what I mean to say is that if a signal is discrete in time domain, it will give us a periodic frequency domain signal, or vice versa, if the signal is periodic in time domain, it will give us a discrete signal in the frequency domain. Now if you look back, by the process of sampling, what we have essentially done to the frequency domain, needless to say, what we have done is that we transform this continuous signal into a discrete signal. So it is suffice to say that the signal is discrete in the frequency domain, and consequently it will generate a periodic signal in the time domain. So this time domain signal will be periodic, and so the limit will go from 0 to n minus 1. Now why 0 to n minus 1 and not 0 to 2 pi or minus pi to pi? Because if you look closely, 0 to 2 pi and 0 to n minus 1 samples, which is this sample, are essentially the same thing. So since we are operating in the discrete domain, it is better to write n which goes from 0 to n minus 1 rather than 0 to 2 pi. It makes our life much easier regarding the calculations. So what we have got here, this relation, this is nothing but the direct DFT, discrete Fourier transform. Very easy if you can get the concept. We simply did what? To summarize, we simply took the frequency domain signal, sampled it in order to discretize the signal, and replaced the value of the frequency domain operator in the direct transform equation of DTFT. This will give us what? The direct transform equation of DFT. It is as easy as that. Similarly, the inverse transform is also derivable from the inverse DTFT, the inverse DTFT signal, which is x of n 1 over twice pi, which goes from negative pi to pi, x of e to the power capital J omega, e to the power j n omega d omega, which is the inverse transform equation for discrete time Fourier transform. Now, in order to get the inverse transform of discrete Fourier transform, x of n will remain as it is. The time period, which is 1 over twice pi in the continuous domain, can be replaced by 1 over n, because as I have said earlier, 0 to twice pi, this length is twice pi, can be replaced by n number of total samples. So 1 over twice pi is rather mathematically correct if we interchange it with 1 over n. Now the rest of the signal, x of e to the power j omega, which is changed in our case to x of k, e to the power j n, omega is replaced by twice pi over n, times k. Now what happens to our summing operator? Will it be a running sum or a definite integral? We must refer to our common sense, what the common sense says. Now, as I've said earlier, the integration operator is used to sum a continuous signal. But since in our case the frequency domain signal is being discretized, it is needless to use our integral operator. Rather, our work will be much easier if we use the summation operator, because the summation operator will suffice. We need not integrate for every discrete values. And what will be the limit of the summation? Where k, which goes from 0 to n minus 1. And now why is the limit of k going from 0 to n minus 1? This is because earlier we have defined the limit of k to go from 0 to n minus 1, which we get from this relation over here. So this is our required inverse transform for discrete Fourier transform. Up until now, I hope there are no confusions, and if that is the case, we shall move forward into the next part. Now, we got our two equations. What I am going to do now is, as per the historical literature, the term e to the power minus j twice pi over n can be written as omega n. And it is quite unfortunate that the negative sign is included here. But this is as per the literature, it has gone down in history likewise, so we must follow that. So if we replace this expression in the equations, we get our direct transform equation x of k, which goes from n 0 to n minus 1, x of n omega n to the power kn, where k goes from 0 to n minus 1, and the inverse transform becomes x of n 1 over n summation, where k goes from 0 to n minus 1 sorry, x of k omega n to the power minus kn, and n goes from 0 to n minus 1. So these two are our modified equations. Now some points are to be noted. First of all, which being, if for x of k n is increased, n over here is increased to n plus capital N, what will happen? If n is increased to n plus capital N, it is quite clear that the signal will remain as it is. That means the signal will repeat itself. As I have said, this signal is periodic. over twice pi. So for x of k, when n is increased to n plus capital N, the signal will remain same as before. Because n is what? Our fundamental period of sample, as shown earlier over here. One period of samples will contain n number of samples. One period of the signal will contain n number of samples. So, secondly, what we must notice is that what will be the case if n over here is increased to n plus capital N. So, what if in x of n, n is increased to n plus capital N? What will be the case? Surprisingly, it will also remain the same. And why is that? Because as I have said earlier, this signal is discrete, so this must be periodic. And conversely, since this is discrete, this will also be periodic. So both the signals are periodic in nature. Now here lies the problem. And I hope some of you will be able to identify what problem I am talking about. We were talking about the problem. The problem is we have considered x of n to be periodic, whereas the essence of Fourier transform dictates that in order for Fourier transform to occur, the signal must be aperiodic. So here lies a gross problem in this form of realization of DFT, which is advantageous in a sense and disadvantageous in another, because if we consider this signal to be periodic, we can get the signal, we can get the value of x of n for k equal to negative infinity to infinity. So if we go beyond this limit of 0 to n minus 1, there will be the Fourier transform, discrete Fourier transform x of k. But what we need to do is limit our range of vision to 0 to n minus 1. Because if we limit our vision to from 0 to n minus 1, the signal here will become aperiodic.